Okay, so our speaker today is Pascal Thomas, and he will talk about examples of disability for Kobayashi geodesics. Okay, so this thing.
Thank you. And I will use both blackboards, so you will be forced to switch. Okay. So thank you very much. It's really a lot of fun to be here. I have the right to even take it off. Yeah, okay. No, I mean, I can be loud even with a mask, but I guess I would be more understandable, more English without. Okay. So no surprise, I will talk about the topic to which I was introduced by Filippo here, which is visibility. So what is visibility? By now, one thing that maybe you know, but you know, there is flowing attendance. So I'll just repeat my take on it. So we have everything I'm going to do in an open set, which is relatively compact in CN. And everything will have to be with respect to k omega, which is the Kobayashi pseudo distance. But I will forget the pseudo very quickly. So, but of course, the definition is good in any geodesic metric space. What's visibility? It's we have two points PQ on the boundary of a metric space. And for me, I am very naive, you know, this is a sort of peasant talk. I'm sorry. Those are points in the embedded Euclidean boundary. I'm not going to look at abstract ones, sorry. They have the visibility property. Well, that should show you the thing for this one. If and only if there exist two neighborhoods of those 2 points, show the same picture. So things may set into the corner here. So I have learned from the experts that those neighborhoods should be egg-shaped, that things can look better. Two neighborhoods of P and Q such that if you take one point in one neighborhood and another point in the other neighborhood, okay, and there exists a compact set. Sorry. There exists K, and we have to understand K is a compact term inside omega. So that any geodesic from X to Y intersects. They have to go here. Okay? And I guess it's called visibility because we are stuck inside omega, and we only see those geodesics that come close to us. So welcome to K. Yeah. So yes.
Am I correct that your neighbors are in Abuja? I mean,
well, yes. Intersection of it. Yeah.
And you're taking genetics with respect to the Kobayashi.
And I only have one distance, and I have actually, of course, a metric, which is the infinitesimal metric. And I create by using this metric, okay, which gives rise to the Kobayashi distance by integrating over rectifiable curves. Yes, the usual setup. I did not repeat everything, it's true. And so you know, this is an invisible curve, something that stays too close to the boundary. That's the sort of intuitive picture. And how is this related to Gromov hyperbolicity, which I will touch upon briefly. Gromov hyperbolicity tells you that every triangle is thin. Thin meaning fixed size, in the sense that one side of the triangle is always in a fixed metric neighborhood of the union of the other two sides. And so how does Gromov hyperbolicity imply visibility? Well, this is one. Now let's think we don't know the geodesics, and we take base point which is inside omega I, our compact K, and we certainly have geodesics. Okay, let's assume we do. I'm a geodesic space. I will take later on hypothesis on omega that make sure that we do always have geodesics and that I can be lazy and forget about the more refined notion that Gautam Barari explained to us of almost geodesics. I will forget about this for today. And then I'm trying to see where the geodesics can be between X and Y. And my hyperbolicity tells me they have to be in the union of those two sausages. Okay? And if I take this, I am in this union, and if I look at what's happening when I'm here, well, those two ends are disconnected, of course, by some distance, and we do have, if we have a geodesic between X and Y, it has to go through here, and so because it's connected, it has to hit the compact set K at some point. I mean, some compact set K at some point. So this is a picture only, but it can be made rigorous. So this is how hyperbolicity, Gromov hyperbolicity, implies visibility. In fact, I think, but this only occurred to me recently, that visibility can be expressed in terms of a condition on a certain small subset of all the possible geodesic triangles, but not all of them. Yeah, so, and we will see, of course, examples where we have visibility, but no Gromov hyperbolicity, otherwise it wouldn't be interesting, right? Okay. Now some things are known about Gromov hyperbolicity. I'm checking black holes.
So is it independent? So the Gromov bar, but it is clear that the other bounds it's still implies visibility. You don't know. You only know F omega dimension.
If I only take this naive definition with points in the Euclidean boundary, does it imply the regular visibility? I don't know. Does it imply the visibility with the abstract boundary? If the two boundaries are different, I have to say I have not tried it. Filippo knows it maybe. It's probably different. So let's just say that this is my ad hoc definition for today.
I have another question. So this definition is not intrinsic about the geometry of the domain. I have two biomorphic domains. If one has visibility, the other one is not.
You are right. In particular, if I fold the domain upon itself, so that there is only one point in the Einstein space which corresponds to two ends, for instance. Yeah. So I will avoid this kind of thing because very quickly I will get into domains which have some C1 or C2 defining function, and then in that case, this kind of thing doesn't happen. But yeah.
Maybe I can add. Morally, the point is that if your domain is Gromov hyperbolic and then you have visibility with respect to the Gromov boundary, of course. And then it depends if this Gromov point you can associate somehow points on the natural boundary of the domain. If these points, you have two different points which correspond to the same Gromov point, then you don't have this kind of visibility. That's the result.
So maybe there is a relation between, you can define visibility for any quantification actually. And then maybe there is a relative quantification is bigger than another visibility.
That's okay. That's an interesting question. It's not the one I will talk about today, but yeah, okay. All right. So now, okay. Now, let us reduce the space of possibilities considerably. So omega will be. We have, I think, a C1. Okay, so let's say it has a C2 column at least, and it is convex. Convex is a very strong restriction, and in that case, there is this great theorem by Andrew Ziller that omega is Gromov hyperbolic. So I always mean for the compaction distance. And oh, by the way, it's also called. Okay. No boundary anything for me. Yeah. So I just look at this. Whenever this is boundary, it's more or less mean that it's given by some defining function defined in the neighborhood of distortion. So omega is probably formed omega is a finite type. Okay, in Zimmer was doing it for domain, but I think we can deal with some less smooth sensitivity. Okay, I have to look at the picture.
I think it says that if you have no regularity, there is an analytic disk on the boundary, then it's not.
No, sure. But of course, if there's an analytic disk on the boundary, it's not finite time. And it does give examples where the thing fails if it's only C11 maybe or no, C01, something like that. C01. For C01, I'm pretty sure it fails. Something of that sort. But there's a big gap between that and infinity, okay? I mean, and finite type here, I will take the naive definition of finite type, no vector field for me, right? Finite type just means this. For convex domains, it's a specific thing for convex geometry, convex domain. Nothing I say should be, extended beyond this. You take L, a complex affine line. And you take tangency here, P, and you take the point P prime on the line, the distance from P prime to omega r should be on the order of P minus P prime to some r. Okay. And typically, of course, it could be greater than 2 because this is a tangential complex line, of course. It doesn't touch omega, but it touches omega bar at the point B, okay? Maybe more.
Is that not the lot of data convexity?
I'm not going to instruction, so I cannot say.
This is the kind of assumption that Gromov has in the case of the geometric equivalence.
All right. Good. And so this is the aspect from the outside. But from the outside, we know that your boundary omega is going to move away from the complex tangents, right? Only the complex tangents. That leaves out a part of the real tangent space. And there's also an inside version that more or less tells you you can put in various subatomic size. And the size, of course, is what this picture suggests. I will not write it for the moment. But you know, if you are at distance delta from the boundary, here this is big delta to the 1 over n. And the more n is big, the more the domain is flat, and the strictly to the convex case corresponds to n equals 2. Yeah? So this is very nice, and there's also a nice extension in C2 for omega pseudo-convex. Then, of course, it's a different definition of finite type, which is relatively valid of time. So I should read this paper someday, but so you do, I guess, this implication, right? Finite type implies. And the numbers is not known, is it? No, not yet. Okay, but so this is still, you see, there's still a lot of work to do in the general case of this, but it's progressive. All right, now, as we have seen, I guess it was maybe yesterday, there are examples of domains which are not finite, but which are specific. And the major family of example is the Goldilocks domains of Barralin and Zimmer. And I will not give you the general definition of them, but at some point I will show you in a special case what it corresponds to. All right. So that's hyperbolicity. And now on to some easy phenomena. One well-known obstruction. So how did this theorem come to be? One well-known, at least well-known, the first obstruction that was found, and I guess it was in a paper by Hervé Gossier and Sechadri, yes, was what happens if your convex domain has got a piece of a magnetic variety inside it. So you see, this is the worst case. If you have a piece of a magnetic variety inside it, well, first for convex domain, this variety, has to be a straight line, and or contains a straight complex line, and you should have a complex face. So you should have a picture like this. Where this, and you can be smooth, right? It has to be convex. So, and this is a complex line. Okay? And this is obviously, well, obviously, no, maybe not so obviously, but this can be seen to be an obstruction to both hyperbolicity, that was Gossier and Sechadri, and visibility. And why is it an obstruction to visibility? Well, because you can, roughly speaking, put in a polydisc in here. And what happens if you take your points P and Q inside this disk? So this is a complex disk. You can providing slightly speaking regularity, put in here a complex disk and say, well, inside this, now you have to understand that this was real dimension, the white thing is real dimension 2, and the orange thing is real dimension 1. You put in a geodesic for the Poincaré. Let me enlarge it. And here, those 2 points are Q prime and P prime. Very close to K and Q. They are inside my neighborhoods U and J And in fact, it's easy to see then that this will give you maybe not a geometric, but some curve which shows that the distance between P prime and Q prime is bounded by a fixed number. And on the other hand, there is this very important. So, as usual, I'll call it the coefficient. A very important estimate. If omega is convex, then the Kobayashi distance from any base point to any point Z has to be more than 1/2 the logarithm of 1 over delta omega of V. Well, minus a constant possibly, which depends on many things. And it blows up near the boundary as 1/2 of the logarithm of 1 over this quantity, which is defined. Distance, Euclidean distance to the boundary. Well, so on the one hand, if you had to go to a complex set, you would have to go to 2 points here. And then you would have to go and have a big distance, but your distance is actually bounded, so no way. All right. It's not, you're not going to have your geodesic going back to the site, because that's not a geodesic, it's much too long a path. Okay? So no visibility if you have a piece of complexities in the boundary. So now the question comes, what is it conceivable that this theorem, could be equivalent to, so examples of visibility with infinite line. So you see that this finite type definition is a definition of a point. Right? And for each point P, you can define the type of the point. So the first question we ask, if we have a convex domain with smooth boundary, and if we have one point of infinite type, we know it destroys Gromov hyperbolicity. It doesn't destroy visibility. Well, no. So that's going to be. That's an equivalent by Kobayashi by Gromov. So let omega convex bounded is and the omega smooth. But let's say same failure, I'm not sure if it requires that much. And with only a finite set of points of infinite type. So, except for a finite set in the boundary, all points are of finite type. Okay. And then we make the domain smooth enough so that the type is has got nice domain continuity. It's going to be locally bounded outside of those points of infinite type. Then for any PQ in the boundary of omega, they enter. So if this finite set is not empty, of course, omega is not Gromov hyperbolic, but it has this visibility property for any pair of points, including the points of infinite type. It doesn't matter. Okay, so that's an example which is in a slightly different character from the Baranitzima example, the familiar example, should I say, because here we do not say anything about you know, how infinite the infinite type is. That sounds ridiculous, but you know, finite type sort of measures the speed of the order of contact between the domain and the tangential complex tangential line. And then if it's an order of contact which is tighter than polynomial, smaller than polynomial, it would be exponential of many orders, right? And the condition by Barani and Zimmer, the Goldilocks condition, tells you this is exponential of type minus c over x somehow, if I may say. But you know, we could have minus c over x squared or minus c times exponential of x or whatever. Exponential of whatever x, and it would not change anything. There is no quantitative consideration here. That's a bit different. Okay. Yes.
And is it easy to find an example like that?
Well, you can construct it. There are many. Many people have looked at models of domain with only one point of infinite type. It's relatively easy. And generically, you have finite type, because generically a derivative can be zero or you have something flat. I mean, things like that. So. If it's a smooth set, of course, if I take the bi-disk, you have points which are either, you know, not smooth, and then you can say merge, or you can say they are type 1 if you want, and then sets which are on analytic faces because it's a bi-disk, and then almost all points are of infinite type. But let's say that we exclude this sort of gross case of having a complex space in the boundary. Okay, because that one is set up. In fact, yes. If it's smooth, generically the type is 2, and that's it. And it's enough for it to be C2 smooth, right? If you just think of type as order, it is this type. So that is one thing. I should maybe give you an idea of how it's done, but yeah, I should. How does it work? It works in the following way. You may have points, maybe even your points P and Q are both of infinite type, you know. But let's assume that we have points of infinite type, and then we go by contradiction. We try to think what would happen if we had points, so we call them x and y again, very close to P and Q respectively, and a geodesic joining them that sort of hugs the boundary, that stays very close to the boundary, that's, you know, like a low flying aircraft. And because that's the only way to avoid all compactor, right? So, and then when you look at a thing like this, what happens is that on the one hand, you know that you have to have big combination distances because in this complex case, one thing that I use all the time is that my infinitesimal distance. So now it's metric, it's a symmetric on its own vectors, and x is a vector. Will be comparable to the inverse of the distance, the directional, the complex directional distance that I should find this to delta omega x is the smooth of positive radii, such that a disk of complex disk, one-dimensional complex disk of radius r, centered at z, carried by the line with vector x starting from z, so it's still contained in omega. So z plus r plus r lambda x is contained in omega for any lambda in the disk. Understand this directional distance to boundary, and so in complex domains, sort of this becomes very simple, very easy to understand. And what happens is that finite type, so time less than n in the region, is that scalar of I have to say implies that we will have this delta is at least something like okay. And x so I want my kappa omega to be big. So that okay, I have to think of it, make it look at my nose. Smaller than something. Yeah. So delta omega z, well, yes, smaller than this, and then kappa omega will be big. Because you see, if you had, in the extreme case where you had a disk in the boundary, a convex disk in the boundary, this directional distance could become big like a constant, no matter how close to the boundary you are. But then it's not the case, so kappa omega is forced to be big. So as you move along with geodesic, you are forced to pay a certain price. And by comparing this to the fact, so yeah, and here I can assume that my type is less or equal to n because I am away from this finite set of points of infinite pi. And so there is a minimum length, and as delta, which is the distance to the boundary, becomes smaller because I take a larger and larger compactor, this becomes huge. And on the other hand, I also know that the potential distance from x to y is less than something like log of 1 over delta omega x plus log of 1 over delta omega of y. And by comparing on that, I found yes. By comparing on that, now there is some work to do. There is some work to do because I have to do this along the thing for infinite points. And Paganini and Zima had a similar thing where there are less caveman and where they are a bit more sophisticated. They use derivatives, just use sound constellations. But anyway, you eventually get to the fact that this distance between x and y, or between xj and y to y, xj, xj plus 1 along the thing, has to be too big compared to what it should be when you look at the estimates. And that's a conversion. I'm not telling you this is a clean proof or anything. It's just the engine what makes it work. Okay. I will try to refrain from proving too much now. And I want to look at what's happening in a few examples of non-discrete sets of points of infinite type. Okay, I have a little bit of time to do that. So I'm saying Barani and Sima, of course, there is difference, but they are using a similar engine to look at geodesics that will be pushed to the boundary and get a contribution. But they use a global bound on kappa omega, which is what they call the boundary solution. To say it in 2 words, right? I mean,
something on the statement that we did here. So the statement was just like for the point, there are no like in the final set of points of infinite type.
No, what happens if you take any 2 points?
Yes. No,
They could be of finite type or infinite type,
yes.
but you can assume both of them are infinite type,
Yeah.
and assume there's a few in between. You always find a little open region which is away from the infinite type. And on this little open region, your type is bounded.
Yes.
And you do your estimates there. Because it's, you have to move from one besieged fortress to another one, and you have to cross enemy territory. So over this finite type territory. And remember that I always assume that I'm away from an arbitrary large compact, so I'm very close to the boundary, I can work very close to the boundary. So over this piece, where the type is bounded, I do my estimates and I find a contradiction. Yeah?
Okay.
The other way is just to construction some open. The other way is just to see all districts get local chart, and then you may use also the result by it's not like
Yeah. So in fact, we stated this theorem with a finite set of points. One could probably, with a little work, try to take a hypothesis that would be exactly the one to make sure that your geodesic crosses an open set with bounded type. Okay? So, for instance, if you have an infinite set of points, which would be a convergent sequence with a limit, that would also work actually. But well, we were lazy. The thing is, what will prevent you from doing it is if you have a continuum of points of infinite type, because then your geodesic would just follow the path, right? Like your low flying airplane, following a road. Yeah? So now I will give you 2 examples of roads. So now, okay. My
because the condition counts. You have 2 floating points. So you can
well, okay. We do that, of course, but I think it's careful. Yes,
I say that because that's
yeah. We just have a whole set of points conversion to 1 point. Things like this.
that's the first thing.
Yeah, I think it would still be true that the geodesic has to cross an open set where the type is bounded.
It's not fixed because father, we cannot fix it. But
You take 2 points.
they detect that the relationship.
Well, take the derivation point and some other points.
So,
It still has to cross some territory where the type is bounded.
yeah, it's more and smaller.
Oh, yeah. But remember, in the visibility definition, the compact of K depends on K. Depends on
I
K.
agree, but you have to prove that for that accumulation point, you are. What they happen is that.
But when you take the accumulation point, and then you take some other points.
Yes, but you are accumulation point, that's where the problem is now. You may have to go far away to very far away from the compact.
But the genetic has to be.
Yeah,
Anyway.
it's not.
It should be yes. But anyway, so now I want to give examples where I have Points of interest like in a convex boundary, and you can be sure that it has to be a straight line or contain a straight line. If it's a curving one, but that's the point we also prove it. So let me just take very simple local models, right? Local models. So there will be one has to choose coordinates. So how do you choose coordinates? But we do. And so there will be original form plus more stuff. Okay, I'm writing it this way. I will not maybe always follow it, but anyway, it's some function of anyway. In general, it's some function of the real part of Z2 is bigger than some function of Z1 and the imaginary part of Z2. Okay. And so for the moment, this is C, this is R, so this is imaginary part of Z2. This is the real part of Z2. So you see there is some unfairness here that this represents a complex line. And this represents a complex line, sorry. And so now I will draw two examples. The first example is a simple one. It's something like this. The boundary d omega. So you know the tangent space d omega to d omega at 0 is equals I r. Right? So it's I r. Coordinates very close. Sorry, I should call it 2, the example 2, because it's less interesting somehow. This tangent space intersection, the boundary itself is now a line which is right. So, and if something, let me say, this is an example, of course, now the others, but real part of Z2 is bigger than some psi of modulus C1 squared, it takes infinity, and psi is an increasing function over I don't what is squared. Okay. And then in that case, psi can be anything. It can be exponential of -1 over x squared, which I want. We always have this speed. Now, of course, I did not define in detail what my omega is. One has to close it up, you know, make it bounded, smooth it out, whatever. I mean, this is just a local piece of example, but with a local piece of example on the web type, psi can be as flat as you want. You have a whole line of points of infinite pi. So, you know, let's say psi of x is much less than x to the n for n or near 0. We can do that. Yes, we can do that. So to have a flat points, infinite time. And but of course it's also flat in this direction. So in this direction I don't care because this is not a complex direction. The complex direction here is the one, the Z1 direction. So if I take psi equals the identity, for instance, it would not be equal to finite, right? But if I take psi very small, it would be pointing finite. But it doesn't matter what psi is, I always have visibility. And maybe this is not a proof at all, but I will just give you a feel good argument. Suppose P and Q are on this line, and this is what problems are, right? We know it's and then take X and Y just above them in the complex line here. Then this is like a half plane. And if you take the geodesic, it will be like this, right? Because the geodesic is a half plane. It has to go out by a fixed amount, which is roughly speaking on the order of the distance. So, this is not a proof. Yeah? There are many other points that can tend to keep you need to do a bit more work, but that is the idea of why that is not. Now, example one. I'm sorry, I only have 4 minutes. So same setup, but the intersection line will now be one real dimension out of this. So I need to change my picture a little bit. So this will now be in this direction. I'm going to put the real part of V1, I think. Well, actually, it's the imagine part of that. And in those two directions, imagine that this is a dimension 2. You have imagined particles in 2 and 4 and the real particles. And we still have the real particles in 2. Okay? And my omega now. Look at this. And we have contact along the orange line. And so the equation is 0.2 the side of 0.01. First, we discuss the element of the and here, if psi and x less than e to the minus pi over 2x, I believe low visibility. But if psi of x is more than e to the minus c over x to the beta, so it has to be bigger. So I need beta less than 1. Then you have and this is by, well, the easiest way to prove it is by dividing it. And this is not optimal, but I only have one blackboard. Okay, so there would be a condition with integrals, but I will not bore you with that. And the way that you prove that you don't have visibility is that when you see we have a complex line hidden in there, we only one dimensional quantity. So take something parallel to this complex line here, and we cut off this part. This valley, we cut off this valley, we put water in the valley. So this rectangle is in the complex line. This rectangle is long and thin, but the proportions are like we have -1 so if the height is epsilon, it's epsilon amplitude above the 0 level. So this is a case to make the conformal mapping in extra computations, and you find that this will give you something. Drawing a segment inside this between 2 points which are there at epsilon level above the ground level will give you something which is shorter than the standard geodesic, but then estimate for the distance that you have from logarithm, so you might find that stays close. Okay, so that's the idea. It doesn't satisfy the Harari's condition. Well, this one satisfies the barrel, this one does not. If you put it in the integral condition of barrel, and if you convert it here, it is the BC condition here would translate into the integral of psi minus 1, the inverse function, the reciprocal of the inverse function of psi, du over u conversion is 0. And then you can work out the thing.
Here is example where the direct condition, the local condition is not satisfied, but however we have visibility.
Well, when we omit a finite number of points,
Such a simple example. It is.
I cannot recall. I'm not sure because.
Okay, but that's what it is.
So we finished it a little bit of the time.
Okay, so thank you for your talk, Pascal. Are there any questions, comments?
Can you follow the contact set in terms of distance to the boundary, in terms of beta?
I don't know, because like parallelism, we proceed by contradiction, and so we haven't tried to see. We let things tend to 0, and we haven't tried to see where things will break down. It's a bit complicated. I'm not sure. One thing I would say also is that for those people who are using several complex variables, of course, the first example is a complex normal curve in the tangential space. The second example is the complex tangential curve in the real curve in the complex tangent space. And then when you have a complex tangential real curve, you have to pay attention to the other function. That's the goal.
Okay, I see that Gautam has a question.
Gautam, can you unmute?
Yes, can you hear me now?
Yes.
Yeah, Pascal, hi.
Hello.
So since there was a bit of an echo, there were a couple of things that I couldn't follow, but this pertains to example number 1. So you were explaining some point about how even if one has much more than just a finite set of points that are infinite type points in the boundary, one can still show visibility, in fact, visibility for any pair of points. And because of the echo, I couldn't catch you. What I did understand was from the proof analysis that you gave that if one had a complex tangential curve in the boundary along which one is of infinite type, then that's possibly bad.
Yes.
Now, looking at your example 1, is one able to formulate a general theorem that if one has a curve that is an integral curve of the complex normal field, so all your infinite type points, whether it's a continuum or not, is confined to such a curve, one has visibility everywhere. Can example 1 be jazzed up to get to that sort of a conclusion?
So you mean the first example that I gave, yeah, with the complex normal curve? Probably yes, because I think it can be proved, but it falls under your condition, the Goldilocks. Because even though we have infinite type, this is in one direction, and when you look, well, no, maybe not the Goldilocks, but it means instead of looking at the curvature avoidant infinitesimal metric in all directions, you have to look at it in some tangential directions. And the fact is that you have a very big order of contact in this example, which is in the second blackboard, the one that maybe you don't see here, this one, yeah. There seems to be a very high order of contact in the real direction, but in the other direction there is not such a high order of contact. So I think it's probably not a very difficult one to do. But I think the more interesting case is the last one I gave, where there is a dichotomy between the orders, between various orders of contact. And that one is in the paper with the people.
Yes. That is completely new to me. True. Thank you.
Okay. Are there no questions? Okay. I have a question. Who found this visibility option? Sorry? Who found this visibility option?
It's all, I mean,
I think, I know, maybe, but at least it's all, but it's saying the theory remind the manifolds of non-positive curve. Work of the underlying.
So let's try the speaker again. Let's start in 30 minutes.